Alhamdulillah. I hear voices from you, dah rasa lega walaupun tak nampak muka lagi. Can I see your faces? I hope you are all at your places at the moment. Okay, so you can see your classmates on your own screen because I am broadcasting your classmates. So you may guess who is your neighbor. Kalau suruh saya guess memang tak lepas lah. I can only, kamu kena buat quiz kat saya. Bagi hadiah hebat-hebat baru saya bertungkus lumus. Kena teka sebelah-sebelah ni nama siapa. Unfortunately, my picture is no longer on sits together mode, but you can see me somewhere. So this is how I'm supposed to be stationed at the front of your class. Betul tak? Nampak tak? Before this, I was together with you. They randomly positioned, duduk kat belakang lah, duduk kat tengah lah. So how am I going to teach you? So now you can see clearly that I am stationed at the front, but unfortunately you could see my back. But I'm actually looking at you, macam tengok tepi-tepi kiri-kiri gitu. Yeah. So as a start, that should be already the best way that I can do to simulate face-to-face classroom. All right. Hey, Mr. Raja. Tiba-tiba muncul. Okay, I'm going to change together mode to large gallery. Yeah? Oh, before that, let's take a screenshot. Kita ambil screenshot nak? Tapi screenshot ni I think tak akan nampak muka saya lah because it's broadcasting my photo in video recording Teams but not on my screen. Are you ready to screenshot? Ni siapa atas ni? Yang belakang sekali, atas sekali. Ready ya? Ready? Smile. 1, 2, 3. Okay, kita tengok jadi ke tak. I'm gonna paste it in my chat box. Boy, senyum manisnya. Siapa tu agaknya? Siapa tu agaknya saya kata senyum manis ya? Siapa rasa dia senyum manis? Cuba angkat tangan. Ya, lelaki angkat tangan lebih dulu. No dada, you nombor 3 angkat tangan. Tak sangka. I ingatkan lelaki senyum handsome, bukan senyum manis. So, I'm going to change now to my large gallery. Ya. Hold on. Ya, jadi ya. Saya send. Tapi tak ada muka saya. Okay, changing to large gallery. Okay, can you see all your friends now in large gallery? Yeah, you're in your own box at the moment. You got a wall there between your neighbor. Maksudnya kalau you nak tanya soalan, you kena telefon lah, guna WhatsApp. Guna handphone. So anyway, we're gonna start our class today. And we will start our class with the recitation of doa. Can we have someone? Anyone to volunteer for the recitation of dua? Tengah tunggu, tengah buka PowerPoint sendiri ke? Okay, I'm gonna broadcast my PowerPoint then. Okay. Anyone who wants to volunteer?
No, test.
Okay, Mr. Ezwan.
Yes, betul.
All right.
Can I see the slide later because I can't
Oh,
find the slide.
lupa. Okay. Sorry. Oh, dia tak tunjuk lah slide tu. Hold on. Sekejap ya. Can I share that in my chat box? Sekejap ya. So it's in the chat box. Dah dapat?
Kat ni dah.
Chat box.
Okay, Dr. dah jumpa.
Okay.
Bismillahirrahmanirrahim. Allahumma ja'alni fi qalbi nuran wa fi lisani nuran wa fi basari nuran wa fi sam'i nuran wa ani yamini nuran wa an yasari nuran wa min fawki nuran wa min tahti nuran wa min amami nuran wa min khalfi nuran waj'alni fi nafsi nuran rabbi shrahli sadri wa yassirli amri wahlul 'uqdatam min lisani yafqahu qawli rabbi yassir wa tu'assir ya karim.
Amin.
Sallallahu ala sayyidina Muhammad wa ala alihi wasahbihi wasallam walhamdulillah rabbil alamin.
Amin ya Rabbal Alamin. Alhamdulillah. Thank you so much to Mr. Ezwan. Okay, so we're going to start our class. As you see from the class agenda, we will finish up our topic 7, a little bit more to finish up the part 1. Then I will go into the explaining on the tutorial questions that we have from part 2. And the last part of the part 2 is interstage cooling, which I will explain that in the next class. Yeah. And also I wrote in the agenda today that we will be having our tutorial practice. Once we hear the explanation of the tutorial questions, then we will take our first 5 minutes break. Then I will give you some break, more than 5 minutes, because I have some very small activity, individual activity that you have to do on your own. Then we'll come back after 15 minutes to hear your progress. Yeah. All right. Without further ado, we will start with the topic 7 to continue on the first part. So I will need to go to my PowerPoint. Yeah, hold on. Okay. Okay. Okay, so I'm gonna go to the last slide that we did last lesson, yeah, last week. I just remember it from the last slide that we stopped from my other files, but I'm just gonna go there here at the moment, not this one. I think we stopped here. Okay, that was the last slide. I think that we stopped for your class. Yeah, I'm gonna go back a little bit more. To, yeah, maybe here. All right, just to refresh of what we have done so far. I could still see everyone's on my other slide. Then I will be switching now and then between the PowerPoint and also your class boxes or class gallery. Yeah. So let us just go into this PowerPoint about the steady state energy balance equation. I'm going to start standbying my color pen, blue color, for example. All right. So you see from this small box, that is the energy balance equation that we have we have written it in terms of formula containing the heat energy, yeah, the heat, yeah, from the surrounding, then the work. So we have the subscript with the work from the shaft. Then we have the molar flow rate together with the enthalpy for various species. So you have the subscript I would refer to species. That is for inlet, that is for outlet. Yeah, this is the last term. And the right-hand side is equivalent to 0, which is referring to steady state. I hope you remember what this is. Do you still remember what that is? Why on the right hand side there we define that as 0, and what is that formula? You could refer to your lecture notes if you have it with you. Do you still remember? Anyone? Mari kita tanya. Oh, bersungguh-sungguh Syafiqah melihat nota. So Syafiqah, do you know what that is? This one. Syafiqah.
Ya, Doktor.
The one that I circled it.
Ya, equal to 0, Tuan.
Yes, yes. Why?
Because it's in steady state.
It's in steady state. So what is the formula? So I'm going to go back to my PowerPoint, keep answering. So what is this formula? Syafiqah? Okay, Syafiqah mencari-cari jawapan. Can I go to Amani? Remember that the hint would be we are writing the energy balance, yeah? So when we are saying the energy balance equation is in steady state, we are expressing about energy in the reactor. And we are saying that the situation in the reactor now is assumed to be steady state. So what is in steady state? Itu dah soalan saya tu. Which you write in the equation earlier. Okay, Amani.
Sekejap.
Wah, besar sungguh nota Mashita. Okay, Amani.
I think because Work dan dia tak ada sekejap.
Okay.
Tak ingat lah madam.
Amani dah pergi mana? Amani tak ingat Okay, kita tanya lelaki pula. Afsar. Mr. Afsar.
Ya, Doktor.
Yes.
Jadi,
What is this?
steady state ke?
Yeah.
Steady state
Steady
tu
state.
maksudnya dia punya internal energy tu dah tak ada, dia punya equal. Sekejap. Dia punya internal energy adalah equal dekat masa ni dengan masa tu lagi pun internal energy still lagi sama. Dia punya energy.
Very good. So dia kata, because we are relating that to energy, so we are saying at any time, 1, 2, 3, energy, sama. Are you saying that?
Yes.
Okay, because of that, how do we write this in terms of mathematical formula, Miss Nornada? Okay, Miss Nornada.
Yang D pasal ada E system over DT.
Very good. Very good. So we are saying the change of the energy to the change of the time, which is now equivalent to 0. All right. And in this topic, we use E circumflex, which means total energy. Why we use the word total? Why total? Because ada banyak energy. There are many kinds of energy in our reactor. Give me the example of energy in our reactor. Possible energy in our reactor. Mr. Shafiq. Example of energy in our reactor.
Potential energy.
Oh, potential energy. Now my team is not sure. You tak nampak you punya kawan. Okay, sekejap ya. Again, Mr. Shafiq.
Potential energy.
Potential energy, capital U. Some more.
Kinetic energy.
Kinetic energy. Macam mana kita tulis? U squared over 2. Lagi?
Saya lupa yang apa? Yang ada gravity tu.
Right. Yes, gravity. So I'm gonna go to previous slide. Oh, aduh, sakit ke Syafiq? Aduh, lupa.
Lupa.
Sampai beradu-radu gitu. So I'm gonna go to the previous slide, showing back your formula of your energy balance. Yeah, hold on. Okay, saya tengah duk switch my slide. Sini ke Syafiq?
Betul.
What do you call that? Gravitational acceleration punya formula tu panggil apa? It's written on the slide.
Oh, potential energy. Oh, yang tu ya. Okay.
Yes, potential energy there. Potential energy, yeah. This is kinetic energy. That is internal energy. There are many kinds of energy. We also have the energy of the flow, yeah, mass flow, rate of energy to let the fluid coming in and to let the fluid coming out. See how many kinds of energy in your reactor. All right. And other than that, we also have relating to heat transfer. Then we have work, of course, that work from the mass and from the shaft. Remember, I'm going to the next slide. So we have this shaft. I don't know where I wrote it. I'm going to go to our previous slide, I guess. Here, the shaft, the work from the shaft. Do you know shaft? So let's say your impeller. So this is the motor to drive your shaft. This is shaft. Okay. So the shaft will rotate or having revolution clockwise or counterclockwise. So that will cause mixing. Yeah. Mixing. So that will give you some energy. All right. Okay, so that is why we write the word total, because we have so many kinds of energy. And remember in our assumption earlier, or maybe we have not done that last lesson, but we are going to cover that today's lesson. Yeah, what are the other assumptions that we can make in your chemical reactor? All right, so those are the things that will allow work or reaction to occur in your reactor. Without the impeller thing or agitator, the mixing of your fluid will be very bad. Yeah, this is true, yeah, because this is true story, yeah. My own student in the final year design project, initially when he designed mechanically by drawing the AutoCAD, the design of a reactor, everything's are there except for the drawing of the impeller. Dalam reactor tak ada impeller, ya. So the height of the reactor is quite tall, like 10 meters, but no impeller. So imagine how would the mixing of the components, let's say if we have 6 components, the mixing will be not homogeneous. And most probably the efficiency of the reaction will be quite low. Not even quite, maybe very bad. Yeah. So those are all already expressed in your energy balance equation, which you see here on this slide. And we are now talking about why the right-hand side becomes 0. Because as Mr. Afsar said, through time, the energy stays constant. And Nornada said, now this is how you write that expression in terms of mathematical formula. All right, so we have this steady state energy balance equation. So let's say for this one, by the reaction of reactant A, reactant B, producing product C and product D. So I'm going to go to the next slide, showing you the one that we have covered last week as well with you, having steady state assumption. Now we have Q, work, and blah, blah, blah. So we started to express one by one of these terms, including this, which is molar enthalpy of the species. How much joule per each mole of the species? So we're going to go to the next slide. So this is the equation, how you want to find the molar enthalpy of species I, which are the A, B, C, D, according to the formula, which was written from the previous slide, as you see here. Okay, it's coming up. Yeah, this one, yeah. 2 reactants and 2 products. So specifically for this explanation, we use this as your example of reaction. 2 reactants and 2 products. Okay, I'm going to go forward on how to write the equation of the molar enthalpy. And the molar enthalpy depends on this equation. And what is that equation? Enthalpy of formation of species I. How do you know it's enthalpy of formation of species? Because we have this degree symbol, yeah, at the reference temperature TR, yeah, reference temperature, which is 25 degrees Celsius. So you have this at TR, yeah, reference temperature, plus the change of enthalpy, which is HQ, yeah? HQ for A, B, C, and D from temperature temperature T to temperature TR, yeah? Change of T from, TR to T, yeah? Or vice versa. And still the unit is joule per mole. Each of these, joule per mole, joule per mole. So enthalpy also joule per mole. Now, from that equation, we don't know what is the change of enthalpy. So the change of enthalpy, this one, depends on the change of the temperature, of course. We are talking about non-isothermal. Temperature is not constant. Times the Cp. Cp is the heat capacity for each of the A, B, C, and D, yeah, from T1 to T2. Okay, the question would be, how do we find Cp? That Cp, if you don't have the published data already determined from scientists or published from a reliable article, so you can calculate your own Cp by knowing the coefficients, alpha, beta, and gamma, and that specific temperature. Then you can calculate your own Cp, yeah? Okay, I'm going to go to the next slide. Knowing already that enthalpy is that formula, all right? And now we simply simplify that integral formula from TR to T to here, yeah? Simply open up the terms in that integral form. So ending up, the molar enthalpy depends on the enthalpy formation of the species at reference temperature plus that Cp at T and Cp at reference temperature. Okay, gonna go to the next slide. Now, we already know this one. And the whole term in that full energy balance equation having H, the enthalpy initial minus enthalpy final. As you know, I think I have mentioned this earlier, we can write normally change of the enthalpies, normally H final minus H initial. So this is what is written, yeah? Final minus initial, simply the final minus initial. All right? Simplify this and you finally get that. Yeah, final minus initial is equivalent to Cp times temperature final minus temperature initial. Bring this to here. And remember, in the energy balance equation, we have initial minus final. Yeah. So first, initially, the symbol is positive. Because of that, it will now becomes negative. So this is what you see in the next slide. Initially positive sign, now it becomes negative sign because of the switching. Yeah. Okay. So we're going to go to the next slide. So this is done. Now we're going to go to the last term, not the last term, the final term in the expression, which is the heat of reaction at temperature T, at temperature T, yeah? This is at temperature T. So HRX with the subscript R reaction and X reactions, yeah? The heat of reaction at temperature T, okay, is defined as simply the molar enthalpy with the concentration of that particular species over the A here. Yeah, we have B over A, C over A, D over A. Yeah, simply take that, yeah, respective coefficient. The product, which is D and C, sum it up together minus the total of the reactant, which is B and A. All right, at that particular temperature would give you the heat of reaction. Yeah, the change of the heat of reaction. So that is why we have this change symbol. Why we have this change symbol? Because we have the formula of the total for the product minus the total of the reactant. So this is what you see here. The summation of the product and the summation of the reactant. So that is why we use that symbol change or delta. Okay. So once we have that formula, so this is what we do in the next slide. Replacing this formula, which you wrote earlier in the previous slide, into the main formula. Yeah. But here, this slide first show you if we can write the heat of reaction at the specific temperature, we can also write with the same format the heat of reaction at reference temperature. Since we are referring to a reference temperature which is 25 degrees Celsius, so we insert this value, yeah, with this value, yeah, the degree sign. When you see that degree sign at superscript, then we are always referring to reference temperature. Reference temperature. By using the same format, using the delta, meaning the summation of the reactant minus the summation of that of the did I say reactant? Sorry, product minus the reactant. Okay, product minus the reactant. But now, since we have the degree, because we are saying the change of enthalpy, the enthalpy formation, yeah, at reference temperature. So you have that for each of the species. Okay, the enthalpy formation for each species, the product and the reactant. All right. So here, from each of this, the question would be, what is each of the mole enthalpy? Of course, you can do that by using this formula, which you defined earlier. All right. So I'm going to go to the next slide. So having that formula, and yeah, this and that is the same here. And this is CP for all the I, which is A, B, C, and D. So you have those D, C, B, and A. Then you have that terms, yeah, which are defined as such, would give you the change of enthalpy at the temperature T, at a specific temperature. In this case, the heat of reaction, yeah, the heat of reaction. So I am going to go back to our previous slide to see at the nomenclature that we wrote earlier, yeah. Okay, this one. The heat of reaction at that specific temperature. So I'm going to go forward. Okay. Okay, so this is the defined formula that we wrote considering all the respective formulas in the energy balance, which can be summarized on this slide. Yeah, the heat of reaction for that specific time depends on the enthalpy formation at the reference time, reference temperature, 25 degrees Celsius, plus the change of the CP, the heat capacity at temperature T, and also temperature reference. And the question would be, how do we write the change of heat capacity? The change of heat capacity is written by this formula in this box, showing you the summation of the heat capacity of the product minus the heat capacity, the summation of the heat capacity of the reactant. All right. In other words, the final formula for the heat of reaction for that particular temperature is written by this last formula on this slide. Yeah. It's influenced by the enthalpy formation at reference temperature and the heat capacity for that temperature and also reference temperature. Okay, so I'm going to go to the next slide. Now we are almost ready to use the energy balance equation for a specific chemical reactor condition. Yeah. For example, on this slide, you can see that if we assume that the reactor has a single phase, let's say gas phase, yeah, for both, yeah, the product and also the reactant. And in most system of a chemical reactor, the work of the shaft is not considered. Yeah. In reality, the work of shaft exists. So let's say if you have CSCR, then of course we have this work of the shaft. If the impeller doesn't operate, then the mixing of the mixture, I want to say mixture and mixing, ya, jadi mixing. Inilah dia bila dah bercakap banyak tu lidah pun boleh terselio, ya. So the mixing of the mixture must be done homogeneously by the impeller. Of course, we have work of the shaft. But when we want to solve our chemical reaction condition in terms of the energy condition, specifically, there are a few things that we can assume it to be negligible because we want to go for the conversion, for the change of the temperature and so on. So most of the system, we can say that the work of the shaft is neglected. Yeah. Then, of course, we use reference temperature at 25 degrees Celsius. And, of course, we have A, B, C, and D. Yeah, if we still use that reaction as our example. And we say, of course, for each of the components has CP, heat capacity. Yeah, heat capacity means the capacity of that particular component in terms of heat containing, yeah. The unit for the heat capacity is joule per mole Kelvin. If I'm not mistaken, yeah. If you want to check, I did write that in our previous slide. The unit for the CP, which is joule per mole Kelvin. And you could also use some other units, yeah, for the heat capacity. If you use British, yeah, BTU per pound mole per unit R here. If you use some of the unit, calorie per mole per Kelvin. Yeah, it depends on the unit standard that you use. All right. So for each, I'm going to go forward to the last slide that we did just now. So in the reactor, if we have 4 components, each of the components, the chemical components, have its own heat capacity. This one. All right. The question is, does the heat capacity changes through time? Yeah. Here, we assume that heat capacity for each, yeah, it has different value probably. or maybe all of them have the same value. But the point is that we are saying the heat capacity is assumed to be constant, yeah, doesn't change, yeah. If the number is 10, then 10 always, yeah. So this is what it means. Okay, lastly, we say that the reactants enter at the same temperature, meaning if it's CSCR, we have T inlet, T of that species T naught, yeah, at time equals to 0. T of what? T of A, T of B, T of C, T of D, yeah, most probably T of the inlet, T of the inlet, temperature of the inlet at initial time is assumed to be T naught, yeah? So it's fixed, yeah? Whatever that comes in, the same, yeah? Constant temperature. Bila dia masuk dalam saja, when it is already in the reactor, the reaction starts, then only the temperature starts to change because of the non-isothermal condition. All right? So in this slide, we say assumption number 2, work is assumed to be negligible. Meaning, so this is the energy balance equation. We have work here. So we're going to cross that out with that assumption. All right. Of course, there is work in the chemical reactor. In this case, we want to not to consider it. Yeah. So finally, you'll have that full equation 1128 without considering the work of the shaft. Of course, you have this molar flow rate. Then, of course, you replace that by the equation that we have simplified, and that equation that we have opened up for the heat of reaction at that temperature T depends on the enthalpy formation at reference temperature plus the change of the heat capacity at temperature T and also reference temperature. Yeah, times the molar flow rate and also conversion. So from this equation, from the energy balance equation, we could also rearrange it to find our X, the conversion, all right? Of course, we consider the Q, yeah, the Q whether being removed or added to the reactor. The question is, how do we know the Q it is being added or removed? All right, so this is what we are learning in this topic 7. We got 2 conditions for the non-isothermal condition, which are adiabatic and non-adiabatic. And that non-adiabatic or adiabatic would determine how we write this Q, yeah? The Q for the adiabatic or the non-adiabatic. And we did discuss that in our previous lesson. How do you imagine a non-adiabatic and adiabatic system look like? Yeah, we did discuss on that. And today we will elaborate more, a little bit more today in terms of if you were to design that reactor, yeah, how would you do it? Yeah. So I'm going to go to the next slide. So this is just a slide that we write about the molar enthalpy for each of the species. Then this slide is showing the 1128 that we have derived just now, considering assumption number 3, whereby the work of the shaft is neglected or not considered. And as I told you, you can rearrange and find the conversion of the chemical reactor. All right, I'm hearing the azan at my place, so we are going to take a few maybe 1 or 2 minutes before I finish up the first part, yeah, to hear our azan. Okay, Assalamualaikum warahmatullahi wabarakatuh. We are back. I hope you're also back in your own seats. So I hope to see you as well. Nazrin, sempat pergi solat ke Nazrin? Nazrin? Oh, ingat ke pergi solat. Pergi solat, sempat solat, laju betul. Ah. Macam arwah pak saya dulu katalah, solat laju macam kilat. Zaman muda-muda lah ya, kejar masa je solat macam kilat, laju je. Tunggang terbalik, apa baca pun tak tahu. Arwah mak saya lah, selalu marah. Solat tak boleh slow-slow sikit ke? Laju benar. Okay. So, thank you again. I'm happy to see you again. So it was always at this time that we make a short pause to hear our azan. Ya, hari ni saya pakai headset. So when I'm using my headset, saya macam Najwa lah pakai headset kan. Okay. So tak dengar sangat azan tadi. Bila nak ujung mau dengar. Okay, cepat-cepat berhenti ya. Tapi tak sempat solat pun. So after the class then we should perform our prayer as soon as possible. Yeah. So I'm going to proceed with the PowerPoint. Okay, kejap ya. Okay, so you should now see my PowerPoint slide. We are going to proceed to the next slide, yeah? Okay. All right. Yeah, I hope you could see my next slide, slide number 44, showing you an additional assumption that we can make for our chemical reactor system, yeah, which is adiabatic. Yeah, the rest of the assumption, we have seen that from our last previous slide with the work, single phase, reference temperature, constant CP, and TI, TI naught. And the additional assumption that we want to make for this one is if, let's say, in the reactor, it is considered to be adiabatic. What do you mean by adiabatic? Yeah, adiabatic means the Q in your energy balance equation is now considered to be 0. Yeah, I'm not sure whether this class or the other class which I asked you to screenshot, yeah, the table 8.1 or from chapter 11 and chapter 8 from the 5th edition and 8th edition respectively, the 4th edition respectively. But for an adiabatic system, with that assumption, we are saying there is no Q being done, yeah, for that system. For non-adiabatic system, if I write cross and adiabatic means non-adiabatic system, okay, we say that the Q dot is not equivalent to 0, yeah, for non-adiabatic system. And you know from the energy balance equation, there is Q dot, yeah. If we make the assumption of adiabatic, we are going to choose that assumption, whereby the Q dot is now equals to 0. Yeah, and in the previous lesson, we mentioned about how does this adiabatic system look like, yeah, if we were to design that reactor. And that at that moment, it was just a preliminary discussion on how would we imagine the adiabatic system in comparison to the non-adiabatic system, or vice versa. Now, we know that for the adiabatic system, we are going to make that assumption, which is the Q dot is equals to 0. No Q. We don't add the energy in terms of heat, or we don't remove the energy in terms of heat from the reactor. Let's say we choose CSTR. And you know that there is feed in and feed out. And you know, let's say we have A, B. And coming out, of course, in the reactor, of course, we have A, B. Now it produces C and D. Yeah? If we choose that reaction with 2 reactions and 2 products. Then now here we have the outlet, we have A and B remaining. And of course, your product, C and D. Okay? And now we say we have this A plus B produces C plus D, which is non-isothermal. Okay? Through time, of course, the temperature increases, yeah? The temperature may increase. If it's exothermic, let's say, the temperature changes. And we are not going to add any heat to help it, or we are not going to remove any heat or to kacau that reaction. We are going to let it be exothermic. Biarlah. Sebanyak reaction tu temperature dia berubah. Biar. We are going to allow that to happen. And how are we going to allow that happen? If in your reactor, katakan ni dia punya thickness lah. Okay, my drawing is very bad. So let's say the CSTR is made of stainless steel or SS2 stainless steel lah, katakanlah And that stainless steel has certain thermal conductivity. Remember in your heat transfer class, that K of the stainless steel, the thermal conductivity, unit mungkin joule per meter per second kot. Watt kot, watt per meter second. Bukan joule, watt. So joule per second is watt. Watt per meter second, yeah. So joule per meter second squared maybe. So maybe the K, the unit of the thermal conductivity is watt per meter second. Correct me if I'm wrong, maybe saya tersilap ke apa ke. Alright, and that K is capable, K, bukan dalam chemical reaction, K is specific rate constant, okay? But in your heat transfer, the K is your thermal conductivity for conduction. And the stainless steel has the capability to absorb the heat from the reactor. Meaning, kalau tak ada resistance sangat, the temperature in your reactor from the reaction fluid will be absorbed by your stainless steel. And we are assuming the temperature of your stainless steel is equivalent to the reaction of your reaction mixture. Kenapa? Because the thermal conductivity of the stainless steel is very good. Sampai dia boleh sama lah temperature dia. So kalau kat luar ni, at the outer part of your stainless steel, ni outer, kat outer ni ada air, your environment. And the heat will be transferred to the environment. So we don't want that to happen. We don't want that to happen because we want the reaction to be only in the reaction fluid, tak pergi mana-mana. Then only we can allow effective reaction, yeah. A plus B with the heat exchange and so with the heat exothermic release producing CND, which is good for them, yeah. We don't want that to happen, so that is why I'm going to change the color of my pen to blue, let's say. That is why we add insulator. Okay? Maybe you answered it last week. Because of the insulation, kat situ ada that is adiabatic. So how do we explain the story? So this is how we are explaining the story. Yeah? We want the exothermic reaction to happen in your reaction because it's good. Yeah, we want to allow it. The temperature changes, lagi dia punya X naik tinggi. The conversion increases by the change of the temperature, by the increase of the temperature for exothermic reaction. So we are not going to allow the heat to be released to the environment. So we are adding insulator. Because of that, the Q is equal to 0. Kita tak ada kacau dia. Yeah? The Q maintains. Yeah? There is no change of heat, yeah, between the reaction mixture or to anywhere. All right. Now, going back to this formula, we rewrite the energy balance equation for the X. And you see that the X depends on the temperature and also the initial temperature and also the reference temperature, the change of the heat capacity. Remember the definition of the change of the heat capacity, ya, tadi formula tadi. Explain it in your own words. Make your own story. And also the enthalpy formation, yeah, at the reference temperature. And from this equation, I'm gonna delete the drawing. Tak boleh delete ke? Sekejap, kalau I guna method ni boleh delete ke? Boleh. I'm going to use my pen. So I'm going to delete this so that you can see this clearer, yeah, this box. And also, okay, cukup. Right? So from this equation, at the denominator, which is here, the denominator of the X equation, we got two terms, yeah? I'm going to change the color to red now. This is the first term, term number 1. And that is second term, term number 2. All right. And in first term, we have the enthalpy formation at reference temperature. The second term, this is the first term. The second term, we have the change of the heat capacity. And it says that between those two terms, in the denominator, we are saying as if the second term is somewhat negligible. Maksudnya, ini lagi besar lah. The impact, yeah, the effect of the heat enthalpy formation is greater, yeah, at reference temperature in comparison to the change of the heat capacity. Okay, because of that, I'm going to delete some of the writing. Okay. Okay, I'm going to clear out some of the writing. Okay, now it's clear. Because of that, I'm going to choose blue color. We can say that is negligible. Does not mean that it does not exist. Negligible with respect to first term. And we know this is a specific number. Yeah, in mathematics, we say it's a constant. It's a constant. When you say it is a constant, meaning it is a number. There is some number, yeah? Okay. And we know that CP is a number as well. In mathematics, it is a constant, yeah, a number. And we say earlier that CP is constant, so the number is fixed. Then this one is a number, and theta, of course, a number. In your reactor, what changes is your temperature, yeah? In your reactor here, what changes is the temperature. All right, okay, hold on. The temperature here. Okay, so we can say the X is directly proportional to the temperature here. Temperature here. The X is directly proportional to the temperature at the numerator. Can you see my writing? Ataupun tak nampak dah apa yang saya tulis? Kontanya tak nampak. Sekejap ya. Hold on. Content. PowerPoint. Okay, boleh nampak tak tulisan saya? Boleh saya tulis? Tak keluar eh?
Tak keluar.
Oh, tak eh? Sekejap ya. Okay, dah nampak tulisan saya? Okay, so I'm saying the X. On. Tarik. Okay. So the X kejap eh. Okay, so I'm back. So the X is now directly proportional to the temperature. Okay, you can see that. And we know that the T naught is a constant. And mathematically says as constant, meaning a number. Yeah. What is left is that the X is the conversion is directly proportional to the change of temperature. Yeah. So that is why we have this figure whereby the conversion is depending on the change of temperature, and it is said to be linearly changing. Yeah. So that is why we have the X versus the temperature is a linear equation. Even though we have this complicated equation that you see on screen, but it simply means because of that assumption, the CP assumption, the heat of reaction value, the delta change, delta CP assumption, and all those temperature assumption, we can say that the X is linearly changing through temperature. Yeah, temperature changes in the reactor. All right, I'm going to go to the next slide. Okay, hold on. But first, I'm going to give you some 5 minutes break lah kot. Okay, can we have our 5 minutes break first? Tak sempat pula saya nak tunjuk our tutorial and also finish up this one last slide. I think sempat kot sekejap Give me some time to read up my last slide here for the first part. All right. So we have this adiabatic. We have this equation 11.28. Yeah, the equation 11.28. Then we have rewritten that equation or rearranged for X. Yeah, we got equations there, blah, 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 blah. Okay, temperature, T naught, CP, delta CP, heat of reaction, yeah, at reference temperature and so on, yeah. And we could also rearrange the equation of 11.28 for the temperature, yeah. We know that for the non-isothermal condition, the temperature changes. So the temperature can simply be rewritten and you can see the formula there on the screen. Before we take our break and also short exercise, individual exercise, I'm going to go to part 2 with the tutorial question. It's the energy balance practice. And you can see from part 2, there are tutorial number 1. Then we have tutorial number 2 until tutorial number 5. Yeah. So I'm going to go back to tutorial number 1. The tutorial number 1 has been explained in your lecture notes. Remember, if you flip back your lecture notes, we already have this figure, the change of the temperature for that volume in PFR. I think this is PFR. Yes, correct. This is PFR. And the change of the specific rate constant because of the change of the temperature through volume, and also the change of the conversion through volume. Yeah. And the question asks you to calculate the reactor volume with that specific conversion. So you can simply do that, which very direct. We want to find the V, so we use this Levenspiel plot. To do that, of course, you need that ratio value, the step number 10, as you see on the slide, right-hand side bottom, over this one, over the X, yeah, over the X. So the volume under the area under the curve will give you the volume for your PFR, yeah. So those are the steps from step number 1 to step number 10. So if you go to tutorial number 2, yeah, you can try that at home, yeah. You're already at home, yeah. Tutorial number 1. Let's go and have a look at tutorial number 2. This is where that I want you to do this exercise in class individually today, yeah, before we end our class, individually. We have 2 reactants, nitrogen and hydrogen. And of course, if you use the alphabet, yeah, you know that A plus B, yeah, okay. 2 reactants will produce its irreversible reaction, produce C. And that C is ammonia. And this equation, this question asks you to find the heat of reaction of the synthesis of the ammonia, the heat of reaction. So we want to know how much of heat being produced or whatever. And from here you could identify whether it's an exothermic or an endothermic reaction, yeah, from the final value that you calculate. From here, of course, in writing those steps or formulas from the energy balance, we need to specify certain value, yeah. For example, the heat of formation, the enthalpy formation, yeah, the enthalpy formation for the, in this case, the species, yeah, the enthalpy formation, let's say in at reference temperature. So you may also need to know the enthalpy for the species at certain temperature, or you may need to know the heat capacity, yeah, at reference temperature, or the heat capacity at the temperature. All right. But the information are not given in the question. Does it mean that we cannot solve for the heat of reaction? No. So the exercise today is to allow you to practice finding your own value. Yeah. I'm not going to ask you to directly solve this question yet, but I just would like you to browse the information from Paris Chemical Engineers Handbook, yeah? So if you Google, you could find the Chemical Engineers Handbook by Mr. Perry and Mr. Green. So you can see here, Mr. Perry and Mr. Green, who have created, yeah, who have written this handbook for chemical engineers. Almost all over the world are using the same handbook for references of certain data. Yeah, from this handbook, you could find all these formula in tables or in appendices, yeah. I remember in the 90s, I was already asked to buy this handbook, yeah, when I was studying, yeah. So it's just that Al Faculty didn't ask you to buy this as a compulsory handbook that you should have. But when you have extra money, please buy. Yeah? At the moment, we already see that the availability of the Paris handbook can be obtained by ebook, yeah. Then maybe you want to invest some money. Yeah? In the future, it could be now, it could be in the future, invest some money to have your own handbook. Yeah? You could see that in the handbook, there are various information related to chemical engineering. Yeah? The design, the fundamental theories for all subjects that you learn for the rest of the 4 years. Yeah? So you can do that. So I want you to take the remaining time as your own individual practices. Let's say choose 5 species, yeah? So I did this in the morning class, and one of the questions from one of the student asking me, maybe the instruction was not so clear, boleh ke kita ambil suka-suka hati je species kan? The instruction was to just practice finding heat capacity and also the enthalpy formation, yeah, value. So I just ask you to give any species, yeah. But if you want to take this species from this reaction, which is 2 reactant, yeah, on the slide, 2 reactant and also 1 product, you can do that. Go ahead. Find the heat capacity, the enthalpy formation for the 2 reactant and also 1 product here. But if you have some other reaction, or if you don't have any reaction, yeah, just come up with any species, try to find that value. And assuming that the reactant or that could be the product, yeah, just assuming that, yeah, just for the sake of practicing, the main purpose is for you to see how the chemical engineer's handbook from Paris look like. So this is my point, yeah. I would like you to do that. Very simple practices, but it means a lot, yeah, because we don't have that handbook with us now. Even my handbook is in the office, inshallah, not at home. I cannot show you now, but of course you don't have that handbook. So I want you to have a feel of how that handbook look like by first searching the value. Yeah, most probably you don't get that from the Paris handbook by anywhere. Yeah, only a practice. Okay, I'm gonna give you this maybe 15 minutes for you to do this from 5:30 until 5:45. Yeah. First, take your first 5 minutes break, go to the kitchen and drink some water and then come back to your seats and start searching for that value. So we're going to come back to the room and I just want to hear your expression, your sharing, yeah, how your search look like, yeah. So we'll meet again. So after 5 minutes, after 50 minutes, yeah. Okay. See you. Hello, are you there? Boleh dengar ke? Kita semua dah ke
Boleh.
mana-mana dah. Can I see you on your seat? We're going to spend 5 minutes discussing on that. So I need to see every one of you. Nazrin dah sempat solat kot, Nazrin. Nazrin?
Belum
Lagi
lagi.
Nazrin. Tapi niat tu dah dapat pahala sebab dah pakai kopiah. Sebab kelas Dr. Mizon ni tak sempatlah solat. Aduh. Okay. Right, so I want you to share your progress. Ya, mungkin tadi rehat, you have been to your kitchen or you lie down a little bit, you stretch your body, you go out and see burung-burung kat luar ke, I don't know, ada kucing-kucing ke, pokok-pokok ke, I don't know. Ya, as a break, you know. Whatever progress that you have done in searching for the values of the, let's say, heat capacity or the enthalpy formation or the enthalpy value for this species. Does anyone who wants to share your progress? It can be anything, yeah, not necessarily many things, but I just want to see your progress. Anyone who has tried? Okay, Shadiana, Miss Shadiana.
Belum jumpa lagi doktor.
Okay, belum. Okay, thank you Shadiana. Anyone dah jumpa satu ke? Any species? Let's say any heat capacity? Anyone? Mr. Afsar?
Ya, doktor.
Yeah, have you found any value, CP of any species?
Saya jumpa dia punya table tu. Kena
Okay,
kat page.
very good. The table of what?
Table 2.151, heat of capacities of element and inorganic compound.
Okay, so where is the table 2.1 from? In which
Paris handbook.
in which? Very good. In Paris handbook, table 2.1, which edition, Mr. Afsar?
8 edition.
The 8th edition. Which year of publication?
2008.
2008, yeah. Okay, anyone who has found anything from, maybe is that the latest edition? Kok ada orang lain jumpa ke, ada latest edition lagi? Senyum je Mr. Afsar tu. Maybe you know that there is another edition which is much newer. 2008 kan tadi kan?
Betul.
Do we have 9th edition? Anyone? Do you have 9th edition? Okay, while searching for that, I am going to ask Mr. Afsar to share a little bit what he can conclude from that table. Mr. Afsar.
Conclude regarding apa?
Kita tengok. Itu yang saya nak dengar tu sebenarnya. You tengok table, you got so many numbers, you got so many rows, you got so many columns. So what can you say about the values? You make your own story, Mr. Afsar.
Kalau based on table yang heat of capacities untuk elements ni, dia ada yang saya tengok heat of capacities dalam Paris ni ada 3. Dia ada bagi liquid, solid punya dengan yang satu ni element. So kalau yang saya tengok ni element punya, dia punya heat of capacities dia semua value akan berlainan. Dia macam yang kalau untuk hydrogen 6.62 plus with 0.00081 T. Lepas tu dia punya range of temperatures dia dalam in Kelvin from 0 to in Kelvin to 73 to 2500 Kelvin.
Yeah. So only from that equation, what can you say?
From the equation,
Kenapa dia bagi range from 273 kata tadi? 273 until 2000 bla 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 Kelvin. Kenapa? Tadi berapa value ni range dia tadi?
untuk yang elemen tu saya tak pasti, tapi kalau yang saya tahu kalau water punya biasa dia bagi range temperature kalau dah tinggi sangat. Kalau vapor dia dah akan mungkin jadi superheated vapor, tapi kalau yang untuk elemen ni saya tak pasti. Mungkin dia exist dalam bentuk gas sampai temperature 2 je ke limit.
Okay, you have that range temperature from minimum temperature till maximum temperature is saying that the equation that you see is only valid for that temperature range. Other than above that temperature, then the equation is no longer valid. So this is what it means. Yeah? All right. In other words, you have the heat capacity which depends on the dalam equation tu ada T kan, temperature kan?
Yes, temperature.
Betul? Alright. So it says that the heat capacity changes due to the change of the temperature. Betul ke? Betul ke daripada equation tu, Afsar?
Betul.
Okay. Let's say you choose one component, Afsar. Pilih hydrogen ke?
Hydrogen.
Dalam tu H kot, H. Elemen
H.
tu apa contoh dia? Okay, H. Okay, give me that formula, tak payah campur plus minus. Only the first part. Apa formula dia? Plus minus kan?
6.2.
6.2.
6.62 untuk hydrogen.
Okay, 6.62 plus
0.00081
times T.
times T.
Plus minus ke plus?
Saya tengok dia tulis plus.
Plus saja. So meaning if the T is very low, then value yang plus tu pun kecil. Kalau if the T is very high, then the value of the the value of the second term will also be very high. So dia akan affect jugalah the value of the heat capacity for the H only, hydrogen, H. Ya, elemen hydrogen, H sahaja, H. Ya. What about pilih yang lain?
H, kalau H saja 4.97 saja.
4.97. Ini H2 ke tadi?
H. Yang saya cakap tadi hydrogen gas.
H2 lah, hydrogen gas. Alright. Okay, so at least you can see that the CP is expressed by certain formula. Okay, what about you choose any other component for liquid? Ada tak?
Ada sekejap.
Okay. The rest of you could also refer to your findings from the 8th edition ke tadi? 8th edition 2008 Paris Chemical Engineers Handbook. Yeah, you may also see some other newest edition, which is 2019, the 5th edition. If you find that very good, you would see that there are an additional information or data being added to the latest edition. Now, the exercise today is to allow you to know where to find this heat capacity for various components. And not only that, you should know how to make your own conclusion or your own story. Yeah, how would the CP changes? Yeah, based on temperature, for example. Okay, Mr. Afsar, ada lagi? For liquid,
Untuk
give me one example.
liquid, yang liquid ni saya tengok doktor dia bagi contoh, saya ambil yang satu acetic acid.
Okay.
Acetic acid
CH3 CH3OOH ke?
CH
Dia tulis tak?
acid C2H4O2.
C2H4O2. Okay, C2H4O2.
Yang ni saya nak tanya tadi doktor, sebab value dia bagi C1, C2, C3, C4 sampai C5. Ada value ada bagi sampai C5. Tapi dia punya value yang dia bagi tu contoh macam acetic acid. Acetic acid dia punya value C1 dia 139 640.
Okay.
Itu kira value CP dia ke doktor yang kita nak tambah tu?
Alright. So in the column you got C1, C2, C3 sampai berapa?
Sampai C5.
Okay. Hold on. From the table, do you see any formula? Specific formula for CP in liquid?
Tak ada.
You should be able to see the definition for the C1, C2, C3. C4, C5.
Tengah cari.
Okay, basically you can see a complete explanation about in reading the table, yeah, for the heat capacity. I'm not sure what C1, C2, C3, C4, C5 means, but it should be defined from that table. As we know that there must be a specific formula that is related to the calculation of the CP. Most probably dia tak guna ke alpha, beta, gamma ke, dia define guna alphabet lain ke. So that is what we want to see, from that table definition. Can you screenshot that or copy that table that you see so that you can share it for the rest of the classmate and paste it in the chat box? Boleh
Boleh.
Okay, so we are already at 6 o'clock. I want you to further look up critically how the CP and also the enthalpy formation value, the heat of reaction value, all right? The heat of reaction value, of course, you can calculate by using the formula, but you need to know the values for the enthalpy and also the CP and also the heat of reaction at reference temperature. So please try to find out how are you going to get these values from Chemical Engineering Handbook, because in reality nobody will give you these values. You will need to find these values on your own. Yeah. So this is the purpose of the exercise today. Very simple, but it gives you the door to the world of chemical engineering in using the Paris Chemical Engineers Handbook. Yeah. So I wish you all the best for today, and let's just postpone, adjourn our class to the next meeting, and we'll see again on Thursday. Betul eh? All right. For the rest of the part 2, we got tutorial 3, 4, 5. Please have a look at that tutorial 3.5. If I'm not mistaken, tutorial number 4 or 5? 5. Tutorial number, hold on. 5 needs you to solve it. Even 4, yeah? Tutorial number 4 and 5 allows you to explore solving the problems by using ordinary differential equation solver, which is polymath. But first you have to know how to write the solutions. Then only you can ask the computer to solve for your simultaneously the differential equations. Yeah. So please have a look before we enter the next part, yeah, in non-isothermal reactor design, topic 7. So have a nice day. See you again on Thursday. Assalamualaikum warahmatullahi wabarakatuh. Bye-bye.
Waalaikumsalam.
Waalaikumsalam. Thank you, Doctor.
Thank you, Doktor.
You're welcome. Thank you. Bye-bye.
Bye.
Bye.